My name's Paul Hopewell, welcome back to my shed. In part 6 I showed you how I fitted a tooth on the main spindle pulley gear. With the belt fitted and the headstock fully assembled, it runs without the knocking noise that used to accompany the chuck on every revolution. As you can imagine, I've assembled quite a bit more of this machine, including the gearbox and lead screw. I had intended to show you more of the reassembly, but I'll have to do this at some other time. And the reason why the reassembling video is on the back burner is because the threads on the half nuts are very badly worn. So much so that it's doubtful they could transmit any motion to the saddle. In this video I show you how I went about fixing the problem. What I decided to do was machine out the old thread and some of the backing from the half nuts and replace them with new replaceable threaded liners. To make these liners, the only bit of spare material I had was 2 chunks of aluminium of a similar size. The only problem was that they had a series of small drill holes all the way through at the same PCD as the threads that I'm going to need. Will these little bore holes be a problem? Well, at the time I wasn't really sure. I first started by cleaning up the end face, and then by using an 8mm drill I drilled through. Then I finished the hole to near size using an 18mm drill. Also, before going too much further, I cleaned up the outside diameter to remove the excess material. To finish the bore, I used a long boring bar to the finished size of 20.5mm. This allowed for a good level of clearance at the root of the lead screw. The boring bar I used that could hold a 5mm square high-speed steel cutting bit inside a 20mm bore only just managed to reach all the way through. This high-speed cutting bit was shaped to produce an Acme thread. That's to the dimensions suitable for a 1-inch diameter Acme screw at 6 TPI. One drawback I had was that my Warco lathe hadn't any instructions on how to cut a 6 TPI thread. According to the instructions, 8 TPI was the best that it could do. So after many calculus attempts, I finally managed to obtain the correct combination of gears while using only the gears supplied with the lathe. Initially, the high-speed steel shaped insert was shaped using slightly the wrong specifications. I was obviously not concentrating at the time. And when I tried to fit the finished threaded liner onto the end of the lead screw, obviously it wouldn't go. So I cut it in half down its length to check the screw pitch. It was then that I found out that I'd used the wrong information for the cutter profile. So I went back to the drawing board and reground a new insert to go into the boring bar. You can see here that the tooth profile looks a bit wonky. That's because when it's mounted in the boring bar, the tightening screws tend to tip the insert over to one side slightly. I've got a new toy in my toolbox. I found it in a scrapyard. It's a fully functional shadowgraph, and it's already proving to be a great addition to my tool collection. Using the shadowgraph, with the insert mounted in the boring bar, you can see that the tooth profile is as good as it can be. You can also see that the Acme profile is capable of making a 4mm deep thread. That I can also see here that I need to widen the tip just a little bit more. After recutting another threaded liner, you can see that it screws on with very little play, which is just what I need. What I'm also doing during this process is recording measurements whilst producing this liner to help me remanufacture another liner should I need it in the future. That's the thread completed. Now I need to know how the two components are going to fit together, that is, the threaded liner into the two half nuts. To do this, I need to clean up and measure the two half nuts after they've had their threads and a little of the surrounding material removed. To start with, I made a couple of identical spacers to evenly fill the gap between them while they could be clamped around the lead screw. This ensured they remained the correct distance apart when they were mounted on the milling machine later. I then mounted the two half nuts up against an angle plate to maintain a true alignment to the back face of the half nuts. I then held them in line with each other as they would be in the apron by sitting them on top of parallels. While trying to juggle all this together, I used a couple of G-clamps to grab everything and keep it in place. If this wasn't enough, I had to set both half nuts true to the milling cutter, and the only solution I had for this was to use a finger mic probe on the outside diameter of the worn thread. As everybody knows, the old thread is a spiral, and the probe would at best be only able to access half of this thread outer diameter. And because the thread bore had all but disappeared along with the threads, this was my only chance to get it right. So while I was rotating the DTI, I was also raising and lowering it as dictated by the screwing action. I believe I got the best that I could out of it, and I estimate I got it to within 0.05 millimeters. That's about 2 thou over the exposed thread root. I hope that makes sense. Having got the bore opened out to 29.5 millimeters, 1.162 inches, I changed the cutter to an 18 millimeter 4-flute end mill cutter to clean the top face. I turned them over and cleaned the other end face. The overall span of these two faces is 66.75 millimeters, that's 2.628 inches. Now that the half nuts are done, I can now return to machining the threaded liner. Now it's my plan to make these threaded liners replaceable, and to do this I need to be able to mount and, at an undetermined time, unmount them from the half nut bodies to replace them, without using glue. To do this I came up with a cunning plan. I know that the threads get forced back and forth. I also know they get a threaded rod sandwiched between them. And as far as I can make out, when the half nuts are pulled apart, these threads aren't under any force stronger than gravity. Okay, you can say that gravity is a colossal force, but in this case it amounts to diddly squat. So I decided to make this liner with two opposing trunnions. In the ends of each trunnion, a 5 mm tapped hole by 5 mm deep will be held in place by two short M5 caphead screws. The recesses in the liner bodies must remain true to the threaded bore. For this I use my tube micrometer to confirm that the recesses and the threads remain as concentric as possible. To make the trunnions each at 8 mm diameter, there needs to be a track 8 mm wide centred to the 66.75 mm. That is, not machined at this point. This means I need to make two recesses at 29.37 mm wide, where the furthest ends of each of the recesses do not exceed 66.75 millimeters, give or take 0.01 millimeters. This left an 8 mm wide rib between both recesses that got more machining later. At this point I had to mark out and prepare for the marriage of these components. I mentioned trunnions in the centre of the recesses. These trunnions, two of them, must be opposite each other and correspond to a hole that has to be made in each of the half nut bodies. So a bit of careful marking out or laying out had to be performed. I started with the bodies by standing them on one of the machine ends in turn and scribed a line. Once the true centre line was established, they were re-blued and once again scribed to ensure a good clean scribe mark. The liner was placed on 2 V-blocks and a line was scribed across one end. The liner was rotated through 180 degrees and scribed once more, and by a process of elimination, the true centre line was found. Holding the liner firmly, a scribe mark was placed on both sides. These lines now represent the radial position of the trunnions. Using odd-legged scribes, or hermaphrodite calipers as they are properly named, the centre line of the rib is marked out and dotted. To find the centre of each of the half-nut bodies, I turn to my vernier scribe. The idea was to find the edge of one of the arcs and record a measurement. Then I had to find the other edge of the arc and record that measurement. After a bit of arithmetic, the centre line measurement was attained and duly scratched across the bore. This completed the crosshairs to the centre of the trunnion seats. The top half nut body has an oil hole slightly above the marked centre line that would prove awkward for the drilling operation later. The bottom half nut body didn't have any such issues, so it was dotted. Also, because of an optical illusion, the scribed marks looked as though the centre lines were offset. So I used a pair of dividers to confirm that these lines were indeed central. For the next operation, I need my 4-jaw chuck. Now, I'm a bit lazy when it comes to using the lathe, and I suspect, like so many lathe operators, the 3-jaw chuck is quick and easy to use for most of the time. 4-jaw chucks for the most part tend to be used for irregular work holding, and they often only get used when they have to be used. A while ago I built this 4-jaw chuck assembly and I've used it almost every time I needed to do a quick 4-jaw operation, and it only takes me about 77 seconds to put it up and use it. To machine the trunnions I had to use a bit of cunning to get things set up. The liner was only held tightly in place by the 2 end jaws. The 2 side jaws basically rested against the sides of the ribs after the liner was set up. They were there purely to prevent vibration. I used a Morse centre to set the trunnion position, and this was an awkward one to get right. To position it laterally, it was a case of use the end jaws. To position it rotationally involved a lot of guesswork. I found that using the Morse centre as the measuring and holding device worked best, while the jaws only provided support until the workpiece was set. The trunnions were machined to 8mm diameter, and then the tops of each of them were lightly skimped to clean up. That was the first side done, then the whole process was repeated to form the opposite side. Here you can see that the liner sits quite nicely inside the jaw slide gap and aids any rotational setting that I needed to make. Now it's time to perform the tedious task of removing the 4-jaw chuck and replace the 3-jaw chuck. Back to the mill. The first of the 2 half-nut bodies is presented to the angle plate. The pin that protrudes out of the back at this time rests on top of the angle plate instead of through one of the slots. And a G-clamp provides all the clamping required for this operation. After using a small spirit level and a setting pin, it prepares the positioning for the drilling of an 8mm hole through. The 8mm hole is cut using an 8mm 2-flute cutter. Using this cutter negates the use of a drill that could have possibly wandered off due to an oil hole that previously existed at an offset position. As for the other half-nut body, the process was the same as for the first one. But in the top half nut body, I will have to replace the now missing oil hole with 2 replacement oil holes, but this was completed later. To remove the unwanted material from around the trunnions, I used the rotary table and also used a bolt through it to keep the liner in place. Then again, using a 2-flute end mill cutter set at just off centre, I rotated the index table below it, gradually removing the excess material from between the trunnions. This next bit was a bit scary. I couldn't see it and film it at the same time, so I elected to film as I viewed the process happening through a monitor. After completing that process, I resorted to using a file to remove anything that needed tidying up. Then I hit it with a polishing mop to make it look more professionally finished. Now came the time to put these items together, and I soon found out that I'd cut things a bit finer than I thought. Everything lined up perfectly, but I couldn't quite squeeze them fully together by hand. Rather than use the vise as a press, I elected to use a G-clamp to apply the necessary clamping force that my bare hands couldn't quite muster. Though the clamping force was really quite light, once these items were together, I just couldn't budge them apart. With that, I drilled a hole in the end of each trunnion at 4.2mm diameter by 5mm deep. Then I tapped them to M5 by hand. Using some Loctite thread locker, I secured the cap head screws in place. Then wandered off to the bandsaw to lock the liner into 2, making each unit into fully assembled half nuts. I also dressed both sides up with a file and then with the belt sander to finish the fettling operation. They both cleaned up quite nicely, but before they can be called finished, I needed to drill 2 oil portholes either side of the now fitted retaining screw. With that job done comes the moment of truth. And in my books, that's a nice job. In the beginning, I worried about some holes that existed through the liner material. And my worry was that they might be detrimental to the liner's performance. But they might actually be of a benefit, because after a couple of wipes around the lead screw, the dirt that was ingrained within was captured in these little recesses. So I think leaving them in as a feature is a good thing. Meanwhile, I found another problem in the apron that requires an equal amount of attention. This means I can't assemble the apron and test these repaired half nuts. That's all for now. Thanks for watching. Bye for now.